Think of describing every point in three-dimensional space. Two vectors only span a flat plane. You're trapped in flatland. Four vectors, at least one is dead weight, expressible as a combination of the others, but three carefully chosen vectors reach every point with zero redundancy. This is the Goldilocks principle of linear algebra. A basis is the set that's just right, not too few, not too many. Today we'll pin down exactly how to tell when a set is just right and prove that the perfect number never changes. A set of vectors spans a space when every vector in that space can be written as a linear combination, a weighted sum like c₁ times v₁ plus c₂ times v₂. Consider R3, take two vectors, v1 equals 1, 1, 2, and v2 equals 2, 3, 5. Every linear combination of these two vectors sweeps out a flat plane through the origin. Tilted, rotated, is still just a plane. In fact, both vectors satisfy the equation x plus y equals z. Check. For v1, 1 plus 1 equals 2. For v2, 2 plus 3 equals 5. So every combination, c₁v₁ plus c₂v₂, also satisfies x plus y equals z. Any point of that plane is unreachable. Two vectors in R3 can only cover two dimensions. To fill all of R3, we need vectors that reach in every independent direction. The second property is linear independence. Vectors are linearly independent when no vector in the set can be written as a combination of the others. Equivalently, the only solution to c₁ times v1 plus c₂ times v2 plus ... equals the zero vector is when all coefficients equal 0. This is called the trivial solution. Now let's look at the standard basis for R3. E1 is the vector 1, 0, 0. E2 is 0, 1, 0. And E3 is 0, 0, 1. Place these as columns to form the 3x3 identity matrix. To check independence, we ask, does the equation c₁ times E1 plus c₂ times E2 plus c3 times E3 equals the zero vector have any non-trivial solutions? This is equivalent to asking what the null space of the identity matrix is. Since the identity matrix times any vector x just gives x back, the only solution to I times x equals 0 is x equals 0. The null space contains only the zero vector, so independence holds. Each basis vector points in a direction that the others cannot reach. A basis requires both properties, linear independence and spanning, full coverage with zero redundancy. The standard basis for R3 satisfies both conditions. First, independence, the identity matrix. I3 has a trivial null space, so the standard basis vectors are linearly independent. Second, spanning, any vector a, b, c can be written as a times e1 plus b times e2 plus c times e3. Both conditions are met, so the standard basis is indeed a basis for R3. Now consider a different set of vectors. v1 equals 1, 1, 2, v2 equals 2, 3, 5, and v3 equals 3, 3, 8. It is not obvious whether these form a basis. To find out, we place them as columns of a 3x3 matrix A, giving us the matrix with first column 1, 1, 2, second column 2, 3, 5, and third column 3, 3, 8. The key question becomes, is this matrix invertible? And if so, these vectors form a basis. Form matrix A with columns v1, v2, and v3. That gives us the 3x3 matrix with rows 1, 2, 3, 1, 3, 3, and 2, 5, 8. Now we compute the determinant by cofactor expansion along row 1. The first entry is 1 times the 2x2 determinant, 3 times 8 minus 3 times 5. That gives us 1 times 24 minus 15, which is 1 times 9. Next, minus the second entry 2 times the 2x2 determinant, 1 times 8 minus 3 times 2. That gives us minus 2 times 8 minus 6, which is minus 2 times 2. Finally, plus the third entry 3 times the 2x2 determinant 1 times 5 minus 3 times 2. That gives us plus 3 times 5 minus 6, which is 3 times negative 1. Putting it all together, 9 minus 4 minus 3 equals 2. The determinant of A is 2, which is non-zero. Since the determinant is non-zero, the matrix is invertible. Therefore, these three vectors form a basis for R3. And here is the general principle to remember. M vectors in Rn form a basis if and only if the n by n matrix is invertible. This single determinant check replaces the need to verify both linear independence and spanning separately. One check replaces two. Both the standard and alternative bases span all of R3. Now let's consider smaller spaces. Take just two vectors, v1 equals 1, 1, 2, and v2 equals 2, 3, 5. These two vectors span only a plane through the origin, a two-dimensional subspace of R3. Within that plane, these two vectors are linearly independent and they span the entire plane, so they form a basis for that subspace. The dimension of the subspace is 2. Now let's add a third vector, 3, 4, 7. Notice that 1, 1, 2 plus 2, 3, 5 equals 3, 4, 7. So this third vector is exactly v1 plus v2. That means it already lives in the plane spanned by v1 and v2. Adding it doesn't expand our coverage at all. It only introduces linear dependence. We now have three vectors, but they still span the same plane, and one of them is redundant. Therefore, this set of three vectors is not a basis for the plane. Here's the key contrast. The vector 3, 4, 7 lies in the plane spanned by 1, 1, 2, and 2, 3, 5. It's their sum. Adding it creates dependence without expanding the reach of our span. Now let's test the vector 3, 3, 8. We check whether it can be written as c1 times 1, 1, 2 plus c2 times 2, 3, 5. Looking at the first component, we get c1 plus 2, c2 equals 3. From the second component, c1 plus 3, c2 equals 3. Subtracting the first equation from the second, we find that c2 equals 0, and therefore c1 equals 3. Now we check the third component. 2 times 3 plus 5 times 0 gives us 6. But we need 8, not 6, right? That's a contradiction. The system has no solution. This means 3, 3, 8 is not in the plane. It points in a genuinely new direction, and adding it to the pair creates a basis for all of R3. Every example we've looked at reveals a powerful pattern. Every basis for the same vector space has the exact same number of vectors. The standard basis for R3 has 3 vectors. Our alternative basis also has 3 vectors. And any basis you ever find for R3 will have exactly 3 vectors. This is known as the Dimension Theorem, a deep result that requires a formal proof. Using this theorem, we define the dimension of a vector space as the number of vectors in any basis for that space. R3 has dimension 3. The plane subspace from our earlier example has dimension 2. This theorem also gives us a powerful shortcut. If you know the dimension of a space is D, then any set of D independent vectors automatically spans the space and therefore forms a basis. You only need to check independence alone. Spanning comes for free. Dimension is one of the most fundamental invariants in all of mathematics. It measures degrees of freedom. Let's see how this concept appears across different fields. In differential equations, the solution space has a dimension that tells you how many independent solutions exist. In machine learning, the feature space dimension tells you how many input variables your model works with. In physics, space-time dimension tells you how many coordinates you need to describe an event. All of these are characterized by dimension, rooted in the concept of a basis. Consider our familiar examples. In R3, 3 independent choices pin down a unique point. In a plane subspace, just 2 independent choices suffice to identify any point. The basis gives you the minimal building blocks, and the dimension tells you how many you need. Whether you are solving systems of equations, compressing data, or modeling physics, the dimension of your space dictates its structure. basis and the dimension together form the backbone of linear algebra. Here's your practical algorithm for checking whether a set of vectors forms a basis. Given a set of vectors v1 through vk in some vector space V, here's the flowchart to follow. First, ask yourself, do you already know the dimension D of the space? If yes, count your vectors. If k does not equal D, stop right there. It's not a basis. You have the wrong number of vectors. If the count k does equal D, then check independence. Form the square matrix from your vectors and compute the determinant. If the determinant is non-zero, congratulations, basis confirmed. If the determinant is 0, the vectors are dependent, so it's not a basis. Now, what if you don't yet know the dimension? Then you need to verify both independence and spanning from scratch without any shortcut. If both conditions are satisfied, then you have a basis, and as a bonus, the number of vectors k tells you the dimension of the space for all future checks. One final note for Rn specifically, the matrix invertibility test gives you everything, independence and spanning, in a single computation. A basis is the smallest set that covers everything. Not too few, not too many, just right. And no matter how you choose it, the count stays the same. That count is the dimension.